Hello everybody. In the last notes that we looked at exponential functions. So notes 4.2, we're going to look at logarithmic functions and their graphs. So exponential functions are one-to-one. That means they pass the horizontal line test. Therefore, if they are one-to-one, then their inverses pass the vertical line test. Inverses of exponential functions are called logarithmic functions. So in this video, we're going to be graphing log functions and looking at transformations on log functions as well. All right, to begin, we're going to generate a table of values for the function by interchanging x and y on the inverse of each of them. Then we're going to sketch the graph of the function. We'll identify any asymptotes on our log functions, and we're going to state the domain and range for the log functions and their inverses, the exponentials. All right, so here we have f of x equals log base 2 of x. This is read f of x equals log base 3 of x. Likewise, f of x equals log base 10 of x. All right, so we don't know anything about these log functions right now. Okay, but we do know that the inverses of log functions are exponential. So what I'm going to do is above each of these equations, I'm going to denote the inverse functions. All right, notice that I read log base 2. Base 2. Well, if 2 is the base on the log function, then 2 is the base on its inverse, the exponential function. So g of x and f of x are inverses of one another. So if we have log base 3 of x, its inverse equation is g of x equals base 3. So we have a base 3 on the exponential inverse function. Likewise for the third one, if the base is 10, because it's in the subscript position, if 10 is the base on the log, it's also going to be it's going to be the base on the exponential function. All right, so we're going to use these exponentials to help us understand these log functions. All right, beginning with g of x equals 2 to the x. In our last video, we created a table of values, and so I have these tables down here recreated. So let's use this data table for the exponential function 2 to the x. As quickly as we can, let's generate these y values based on our previous work. So when x is -2 in the exponent position, 2 to the -2, we saw was 1/4. Oh goodness. When x is -1, 2 to the -1 becomes 1/2. 2 to the 0, anything to the 0 is 1. 2 to the first power is 2, and 2 squared would be 4. And what we did is we took each of these ordered pairs and we came up here and we plotted the exponential. So kind of a quick sketch here. If this is 0, 1, I'm going to draw my graph off of this, a little to the left, a little to the right, and I'm going to draw the exponential 2 to the x. Okay, so this is our review. Okay, we're going to label this our G graph. All right, to produce a graph of this log function, what we would do is we would take each of these ordered pairs and we would interchange them. So all these y's become our x's over here for our log function. So we've got 1/4, -2. 1/2, -1, 1, 0, 2, 1, and 4, 2. Again, this is the data table for the function f of x equals log base 2 of x. All right, so this is our numerical approach to the log function. So we're going to come up here and we're going to plot these points now. I think I'll do this in a different color as well. All right, 1/4 -2. Okay, well what I'm going to do is I'm actually going to put the point 1, 0 here. That way I can plot the other points based off of 1, 0. All right, so plotting 1/4 -2. So 1/4 would be somewhere way over here close to the y-axis. 1/4 -2, stay on there, would be about right here. 1/2, -1 next in the data table. 1/2, -1 would be about here. I'd plot 1, 0. Then I'd plot 2, 1. And then I'm going to plot 4, 2, which would probably be somewhere over here. Connecting these points. It's my little arrow. Oh goodness. The graph of the log base 2 function would look something like this. Trying to get that closer to the asymptote of x equals 0. Now, as a reminder, these two are inverse functions. Okay, and graphically, we can see, or visually, we can see that they're inverses because the line of reflection is y equals x. And we know that to be part of the topic of inverse functions. So to graph log base 2 of x, you might want to think about what 2 to the x looks like, and then think about visually reflecting 2 to the x, the exponential, across y equals x, and producing the log function. Another way to kind of think about the log function also is this. Think about specific points. 0, 1 is on the exponential 2 to the x. So if I interchanged 0 and 1 and made it 1, 0, that might help you get started in producing the graph of log base 2 of x. Okay. All right, and let me go back and name this too. This is our f function right here. Another piece of information that we're going to want to consider is this information right here. G is equal to 2 to the x. And if you wanted to call G y, let's call that y equals 2 to the x here. I know that if I'm considering its inverse, that I could switch the x and y in the equation. So if I have y equals 2 to the x, then f could also be indicated as x equals 2 to the y. But if you look at this equation right here that's supposed to name this function, okay, we really don't want to have y in the exponent position. Okay, so in that case, okay, what we do is we get y out of the exponent position and we let y equal log base 2 of x. So just wanting to point out that we actually have two different equations for this log function right here. One that's in exponential form that we got by just switching the x and y in the exponential function. And the other equation that names this red graph or this log graph is in the log form. So this is the exponential name, this is the log name for the inverse of 2 to the x. We're going to be doing some more work with these two forms in a later video, and just wanted you to see it at this point. All right, let's move on to the next log function that we want to graph. Log base 3 of x. Well, it's the inverse of the exponential 3 to the x. So let's come down to our data table right here. Okay, this will be the data table for the exponential 3 to the x. And this will be the data table for its inverse, log base 3 of x. All right, I know we all know how to graph 3 to the x. It looks very similar to 2 to the x, but let's go ahead and generate the data table that we would use to plot points on 3 to the x. So 3 to the negative 2 is 1/9. 3 to the negative 1 is 1/3. 3 to the 0 is 1. 3 to the first is 3. 3 squared is 9. Okay, you can take each of these individual points right here, and as we did in a previous video, plot these points. Okay, I'm going to start with 0, 1. Okay, I know that the graph is going to be a little more steep than 2 to the x, but it has the same basic shape, same characteristics. Okay, and we're going to call this g equals 3 to the x. Or we could also call it y equals 3 to the x, but different than the inverse function, the log function. I'm getting ready for what we did over here. All right, let's come down here and let's switch every ordered pair. So we have 1/9, negative 2, etc. All right, let's see how many of these points that we can plot on our graph. All right, plotting the point 1/9, -2. Again, like I said earlier, I might want to start with, I know 1, 0 is on log base 3 of x. Gives me kind of a starting place. 1, 0 is here. Plot 1/9, -2. Well, 1/9 is going to be really close to the y-axis, and -2 would be somewhere down here. The next point is 1/3, which is about right here, -1. I've plotted 1, 0. Now I'm going to plot 3, 1. It's probably here. And then the last point is 9, 2, but it'd be very difficult to extend and graph 9, 2. So we're just going to draw the graph off the points we have as they suggest the graph should look. Okay, and I'm going to label this my F graph right here. Draw arrows on the ends to suggest that the graph continues, reminding us that these two are inverses because there's symmetry with the line y equals x. And again, to tie in the exponential log form, we know that this is a graph of the log function. Okay, so I could actually go back to this exponential equation, and if I'm looking at an equation for the inverse, I would just switch the x and y. So this time instead of doing equals, I'm going to just do a semicolon. So if I switched x and y here, I would have the x equals 3 to the y equation that represents this graph. But again, like I said, we don't usually use this equation to name this graph because the y is in the exponent position. So a long time ago, the decision was made in mathematics to get y out of the exponent position and call the inverse function a log with the same base of 3 of x. So this is the exponential name for the inverse, and this is the logarithmic name for that same graph. Right here. These two equations are equivalent to each other, they're just in different forms. All right, let's take a look at our last log function that we're going to graph. It's log base 10, so its inverse is 10 to the x, and we'll take the same approach that we did in the last two. So this is our data table for g of x and our data table for f of x. All right, so what does log base 10 look like? Well, it's the inverse of 10 to the x. Let's revisit filling in this data table. 10 to the -2 was 1 over 100. 10 to the -1 produced the fraction 1/10. 10 to the 0 is 1. 10 to the first is 10. 10 squared is 100. All right, plotting the exponential 10 to the x. I'm going to go ahead and plot the point 0, 1. And with the base of 10, the graph gets really steep quickly this way, but it still has the same horizontal asymptote of y equals 0 this way. This is our g function, which is 10 to the x. I'm going to change g to y because of what I'm going to do in just a second, as I did in the previous two examples. All right, let's interchange these ordered pairs. Let's plot these ordered pairs. I'm going to start with 1, 0. And as best I can, I'm going to plot 1 100th, -2. Well, 1 100th is 0.01, which, my goodness, that's even closer to the y-axis. And if I plotted that point at -2, I'm almost on the negative y-axis. It's going to be difficult for me to plot it where it needs to be plotted. 1/10, -1. Well, about right here. I know that's off, but it's, based on the constraints of the graph, it's a little difficult. 10, 1 is going to be way over here. 10 is here, 1 is up here. So this graph is really hugging the positive x-axis. That's my arrow. I'll come up here, pick up these points, and it becomes very, very, very shallow here. Okay, this is my F graph. So we just produced a graph of log base 10 of x. Again, a reminder, if you were to sketch in y equals x, there is symmetry with that line. These are inverses. All right, and to conclude, let's look at the two names for this log function. One way we can name this log function is by switching the x and y. Where am I at? Here I am. X equals 10 to the y. You don't often see that, but that is correct. That's the exponential form of this log function. Okay. Or if you want to get y out of the exponent position, we made up the name log base 10 here, because we have a base here, of x. So log functions are so special that they get two ways to be represented, an exponential form and a log form. All right, now so what we want to do is come down here and we want to fill in some information about what we have in front of us, about these graphs. Okay, I'm scrolling up, but you should still be able to see yours in front of you. Okay, so for this column that we're going to fill in, I want you to notice these subscripts. This E stands for the exponential function. L, of course, is going to stand for the logarithmic function. We just kind of want to make some observations here. So what's the asymptote of the exponential function? Well, it's horizontal. It's y equals 0. What's the asymptote of the log function? Well, it's not a horizontal asymptote. It's a vertical asymptote. And I think we noticed that as we were sketching them. The vertical asymptote is x equals 0. All right, look back at your graphs. What's the domain of the exponential function? Well, the domain of the exponential function is all real numbers. The range, however, is 0 to infinity. Look at the graph of the log function. You can see the domain is actually 0 to infinity, but the range is going to be all real numbers. And I think what we need to point out here is that for these inverse functions, for exponentials, okay, and logarithmics, that the domain is the range on the inverse function, and the range, the y's that are on the exponential, would become the x's on the logarithmic function. All right, so the same situation is going to occur for this column and for this column as well. So the asymptote for the exponential is horizontal. The asymptote for the logarithmic function is a vertical asymptote. Make sure you're doing x equals, not just 0. And then this information will be the same as the previous example. All right, if I just switch these two sets right here, the range is now the domain, or another way to say that, the y's are now the x's, and the x's are now the y's. And just over here, let's just complete this the same as the previous two problems. All this information is going to help us look at transformations of the log functions, and we'll do that in the next video.